Hi everyone. In the last video, we saw how to measure EMF of the cell by using potentiometer. In this video, we are going to see how to measure the internal resistance of the cell by using potentiometer. Let us say we have cell like this. So we want to measure its internal resistance by using potentiometer. Yeah, the potentiometer, which is used to measure internal resistance of the cell, can be represented in a simplified form of circuit like this. Yeah, it consists of long wire AB of uniform cross section in series with battery E0 like this, and rheostat R0, which is kept at suitable position so that a constant current I0 flows through the main circuit. This is called main circuit of the potentiometer. Yeah, in the sub-circuit, cell and galvanometer are connected in series. Yeah, here a known resistance R is connected across the cell with key like this. Key K like this. So this is nothing but potentiometer circuit. So this is potentiometer circuit. Which is used for measuring. Yeah. Which is used for measuring internal resistance of the cell. Right. Yeah. In this, there are two cases. One is when the key K is open. Other one is when the key K is closed. You can see here. Okay. Yeah. So in these two cases, we are going to obtain the zero deflection of galvanometer by moving the moving contact J on the wire AB. So you can see that moving contact J. Yeah. By using those results, we are going to obtain the internal resistance of the cell. Okay. So let me take case one now. Yeah. Case one, in which key K is open. When it is open, what happens? Current will not flow through the resistance R. Okay. So that is the thing. Only cell and galvanometer are going to connect it to the, what is that? Main circuit of the potentiometer. So let me draw the circuit again for this case. So this is main circuit, wherein cell, here we can say battery, rheostat, and wire AB are connected in series. This is called main circuit. Yeah, here when K is open, R is there will not be any current through R. So only cell and galvanometer are going to connect it to the main circuit of the potentiometer like this. Yeah, you can see this circuit becomes identical with the circuit that is used to measure the EMF of the cell by using potentiometer. Clear? So that is the thing. Yeah. So how to measure the EMF of the cell in this case? Yeah. Right. So here we move the moving contact J on the wire AB and obtain the zero deflection of galvanometer. Zero deflection of galvanometer for the particular position of moving contact, so that at that zero current condition or at that zero deflection, EMF, our objective in this case, becomes equal to the potential difference between junction and particular position of moving contact. That's all. Right. Let us say when the moving contact J is at a particular position, let us say 1. Then let us say galvanometer shows zero deflection. That means current becomes zero, right? So the current expression I am directly writing, so that we obtained in the last class. So that is going to be VAJ minus E by R plus RG plus RAJ. So yeah, here R is internal resistance of the cell, RG is resistance of galvanometer, RAJ is resistance of the wire between A and J. Right, VAJ is potential difference between junction and moving contact position. Yeah, J. Right. Now, so let us see here we said already when the moving contact is J is at position 1. So let us say galvanometer shows zero deflection. That means current becomes zero. When we substitute into this expression, what we are going to get? Yeah. So 0 is equal to J is equal to 1. No? In place of J, we have to substitute 1. So right. As LHS is 0, what we are going to get? EMF becomes equal to VA1. Potential difference between A and 1. That is going to be I0 into RA1. Right. So let me make it as equation 1. But what is this RA1? Resistance of the wire between junction and moving contact position 1. So that is given by rho LA1 by A dash. As I used already here, I am using A dash. Rho is resistivity of the wire. LA1 is length of the wire between A and 1. A dash is area of cross section. When we substitute into equation 1, what we are going to E is equal to I0 rho LA1 by A dash. Here I0 rho A dash are going to be constant throughout the experiment. So E is equal to, we are going to get, let me take it as constant as A, I0 rho A1, A dash. So we are going to get A into LA1. So let me take it as equation 2. Right. Here you can see, yeah, here EMF is depending upon the length of the wire between junction and moving contact position 1, for which galvanometer shows zero deflection. So this is measured with the help of scale which is kept below wire AB, like this. So this is a scale. Yeah, divisions are going to present on the scale. So yeah, so here length of the wire between, sorry, in this case now, yeah. So here, so divisions are going to present. Yeah, so this is measured, that is LA1. So LA1 is measured with the help of scale. So right, so this is case 1. Let us go to case 2. Right. Case 2. In this, key K is closed. When key K is closed, what happens? We can see. Let me draw the circuit. So this is main circuit. Yeah. This sub-circuit in which cell and galvanometer are connected in series. So here when key K is closed, this resistance, yeah, comes across the cell. So this is known. Right. So let me name terminals. So this is AE, FJ. Here this is GH. Right. So here you can see, yeah, when key K is closed, what is happening? These resistance also going to be connected to the main circuit. Here you can see this loop, which is consisting of cell and the resistance R, is closed. So when it is closed, what happens? This cell EMF drives the current in it. Let us say I dash is the current that is flowing through this loop, okay, because of the cell, right? Yeah. So let me, so I dash is the current. What is that current? Let us obtain. So for that we need to apply KVL. Let me draw the loop again so that things will be clear for you. So this is cell. Yeah. So here I dash is the current. So when we apply KVL, what happens? So we can see. So here I dash R minus I dash small r plus E is equal to 0. So E is equal to, we are going to get I dash R plus R. So I dash is equal to E by R plus R. This is the current. So let me take it as equation 3. Right. Yeah. So now let us obtain the expression for current flowing through the galvanometer. Clear? Yeah. So let us say moving contact J is at an arbitrary position. So arbitrary position means what? So it can take any value, right? So when it is at arbitrary position, let us say I is the current flowing through the galvanometer or current leaving the junction A, right? So that is the thing. Yeah. Now let us obtain the current flowing through the current flowing from E to G or current flowing through the resistance R. Okay, right. So for that we need to apply KCL at junction E. So when we apply KCL at E, what the KCL states? At any junction, algebraic sum of the currents must be 0. Let us say entering current as positive. So then leaving current is going to be negative. So leaving current is going to be negative. So when we apply KCL at E, what we are going to get? You can see I and I dash are entering currents. Yeah, I and I dash are entering currents means I plus, they are going to be positive, I dash. So IAG is leaving current here, IAG. So that is minus IAG because it leaving negative. So algebraic sum must be 0. That means IAG is equal to I plus I dash. Here let us focus on the junction A. I naught is the current entering, I is the leaving. Let us say IAJ is the current flowing from A to J. Right. Let us obtain IAJ in terms of I naught and I. For that we need to apply KCL at junction A. So what we are going to get? Entering current I naught, leaving currents are I and IAJ. They are going to be negative. So algebraic sum must be 0 from KCL. So IAJ is equal to I naught minus I. Right. So in order to obtain current expression, we need to apply KVL to the loop. Okay, that is AG HJA. Okay, so to make things clear, let me draw the circuit again. Yeah, here you can see. Here, let us say RG is the resistance of the galvanometer, and between A and J, what is there? Wire is there. Let us say RAJ is the resistance of the wire. So this is resistance. What is the current flowing through the resistance? We can see that is nothing but IEG only going to flow through the resistance R. So this is also going to be IEG. So IEG is how much we got from KCL, I plus I dash. Here I plus I dash will flow, right? So that is the thing. And this will part of it, I dash will glow here like this. How much current will flow through the galvanometer? I will flow. Here you can say I dash is returning to the cell, whereas I is going to flow through the galvanometer. That is the thing, right? So here only I current will flow. So what is the current flowing from A to J that we obtained? IAJ, I naught minus I. So we know current always flows from higher potential to lower potential. So we indicate positive sign, negative sign like this. Yeah. Here also positive sign, negative sign. Here also you can see, of course, I already indicated current flows from higher potential to lower potential. So when we apply KVL to this loop consisting of AG, HJA, AG, HJA. So when we apply, what we are going to get? Minus I plus I dash or minus IRG. Here plus we are going to do plus I naught minus I RAJ is equal to 0 from KVL. So when we separate the terms, what we are going to get? I naught RAJ minus I dash R. Yeah. So here I terms you can see 3 are there. So when we take other side, we are going to get plus R plus RG plus RAJ. Right. So what we are going to get? Current as I naught RAJ minus I dash R by R plus RG plus RAJ. So this is the current expression we got, right? Yeah. So let me move to next whiteboard. So we obtain current expression like this: I is equal to I naught RAJ minus I dash R by R plus RG plus RAJ. Right. Okay. So how many equations we have already? Yeah. So we have 2 equations here, and third equation is also there. Yeah. Okay. Now we are going to get this as fourth equation. Right. You can see what this represents I naught RAJ. So for that we need to refer to Ohm's law. So let us say I1 is the current flowing through the resistance R1. V1 is the potential difference across the resistance R1. We know that Ohm's law relates current flowing through the resistance R1 and potential difference across the resistance R1 is like this. Yeah. So here that means V1 is equal to I1 into R1. So in this product I1 R1, what this I1 indicates? I1 indicates current flowing through the resistance R1. Clear? Similarly, in this product I naught into RAJ, what this I naught represents? Yeah, from Ohm's law it represents current flowing through the resistance RAJ. What this product represents? Product represents potential difference across the resistance R1. Here also I naught RAJ product represents what? It represents from Ohm's law potential difference across the resistance. As the resistance is present between A and J, that is junction and moving current position J. So potential difference across the resistance means that is going to be between A and J. So that is VAJ. So this represents VAJ. So we can take it as equation 5. So when we substitute, what we are going to get? Equation 5 into 4, we are going to get VAJ minus I dash R by R plus RG plus RAJ. So we can apply this to I dash R also. What this represents then? That is also product of I into R. From Ohm's law, it represents potential difference across the resistance R. Okay, so that you can see here. Yeah. So what this potential difference across the resistance means? That is going to be between G and H. So that is VGH. Okay, that is also potential difference across the cell. So VGH is nothing but potential difference across the cell. So right. Yeah. So this is going to be I dash R. So I dash R is nothing but VGH. But we know I dash. Okay, from yeah. So this one E by R plus R here. So when we substitute VGH, we are going to get E by R plus R into R. Yeah. In this, what is our objective? So what is our objective here? Our objective is to find in this. So let me take this as equation. Yeah. So this is 6 now. So this is 7. So VAJ minus VGH R plus Rg plus Rn. Our object is to find VGH, potential difference across the cell. Clear? Right. Now, yeah. Here VGH is going to be constant, you can see, because E is constant, the resistances R and R are going to be constant. So VGH is going to be constant. Clear? Yeah. So before going to experimental procedure, let me make certain things clear. Okay. So for that, let me draw the circuit diagram again. So for the case 2, this one. So this is main circuit. So here, so this is cell, and galvanometer are in series, and this comes across the cell. Right. Now, when we move the moving contact J on the wire AB, what happens? Right, you can see here. So when we move the moving contact J on the wire AB, you can see. So here junction A position is fixed. When we move the moving contact J, what happens? Length of the wire between this junction and moving contact position varies. Okay. So this length of the wire, that is between this one and this one, that is LAJ. So LAJ is going to become variable when we move the moving contact. When this becomes variable, resistance which is proportional to length. We know resistance is rho L by A, that is proportional to length. That is also going to become variable. So when resistance becomes variable, what happens? Potential difference, VAJ, you can see from this equation 5. That is also going to become variable. So this is going to become variable when we move the moving contact, right? Yeah. So here R is a variable, this variable, current also going to become variable in the galvanometer, right? That is the thing, right? Yeah. Generally, so in the range of variation of VAJ as we move the moving contact, okay, the VGH here, potential difference across cell is going to present, okay. So let me make it clear through example. Let us say when we move the moving contact, VAJ varies from 0 to 5 volts, right? So let us say VGH is 2 volts, right? So you can see 2 volts is present between a 0 to 5 volts. Yeah, like this they design. So in the range of variation of VAJ, that VGH is going to present. Clear? So that means for a particular position of the moving contact, okay. So this VAJ becomes equal to VGH, okay. So that is the thing. When they become equal, what happens? When VAJ becomes equal to VGH, what happens? Obviously, from this equation, when VAJ becomes equal to VGH, what happens? Let us say this equation 8, right? Current becomes 0. So current is going to become 0. So which is detected with the help of galvanometer. That means when galvanometer shows 0 deflection, what happens? VGH, our objective becomes equal to potential difference between a junction and that particular moving contact position. Clear? So this is the thing. So the experimental procedure is to move the moving contact J on the wire AB and obtain the 0 deflection of galvanometer for a particular position of moving contact. Clear? So that at that 0 deflection, at that 0 current condition, the what is that? Potential difference VGH becomes equal to potential difference between junction A and that particular position of moving contact. Clear? So that is the thing. Yeah. So let us say when the moving contact J is at position 1 dash, let us say this shows 0 deflection. That means current becomes 0. Okay. Right. So when we substitute into the equation 6, okay. So equation 6, this we can take as VGH. I dash is nothing but VGH. Okay. What we are going to get? I is equal to, yeah. So your moving conductor, of course, we can take 8 also, no problem. So I is equal to, here Vaj is nothing but particular position we are substituting now. Okay, what is that particular position? So yeah, here you can see it when J is at 1 dash, what we are observing, galvanometer showing 0 deflection, that is current becoming 0. So when we substitute, what we are going to get? So let me say sixth equation. Yeah, so current becomes 0. So VA 1 dash. Yeah, so this is I dash R. No problem, we can take like this also. R plus RG plus RA 1 dash. Yeah, so as LH is 0, what we are going to get? So VA1, so here I dash R. I dash R is equal to VA1 dash. So this is our objective. I dash R is nothing but VGH. So this is from, yeah, so Ohm's law. So VGH is becomes equal VGH, which is I dash R becomes equal to VA1 dash. So that is nothing but I naught into, from this equation 5. J is 1 dash, RA 1 dash. So that is the thing. Clear? So that means VGH is equal to I naught into RA 1 dash. Yeah. So in this we can take this as equation 9. So but the resistance of the wire can be expressed like this. We have already seen rho A 1 dash by A dash. Here these are all our constants. Let me take it as A. So VGH is equal to A into LA 1 dash. So LA 1 dash. So let me take it in equation 10. Yeah. Right. So here you can see the EMF is depending upon the, yeah. So EMF is depending upon the remaining are all only LA1 dash, length of the wire between junction and moving contact position 1 dash. So that is the thing. Right. So here a scale which is kept below, sorry. Yeah. Here a scale which is kept below wire AB is used to measure the, here divisions are marked, measure the length of the wire between A and 1 dash for which galvanometer shows 0 deflection. So LA1 dash is measured with the help of scale. Right. So we have now two results from case 1 and case 2. We have expression for EMF and potential difference across the cell. Yeah, right. We also have seventh equation VGH ER by R plus R. So let me show you the equation of the case 1. So this equation 2 we can take, and now equation 10 is there with us. Both equations let us take to next whiteboard. So what we have, E is equal to ALA1 from case 1. This is equation 2. And VGH is equal to, we know, ER by R plus R. This is from equation 7. Is equal to A into LA 1 dash. This you can see. So equation 7. So this is what I have taken. Yeah. So now, so when we take ratio, what we are going to get? 2 by 10. Yeah. So we are going to get R plus R by R is equal to LA1 by LA1 dash. Here you can see from this equation. So here only E is there, here R by R plus R there. This is going to be little less than 1. Okay. Yeah. So that means here we can take E into 1 like that, we can take it is little less than 1. That means here A is common for both. LA1 dash is going to be little less than LA1. So that you can observe in the experiment. Yeah. So when we take ratio, what we are measuring, 1 plus R by R is equal to LA1 by LA1 dash. So R by R is equal to, when we take that side, LA1 minus LA1 dash by LA1 dash. I am directly writing. So R is equal to R into LA1 minus LA1 dash by LA1 dash. So these are measured from the scale, LA1 and LA1 dash. So this is known. So by substituting, so we can obtain the value of internal resistance of the cell. Here in the experiment, okay, so in the experiments we are only measuring, or in the case 1 and case 2 we are only measuring LA1 and LA1 dash and obtaining the internal resistance of the cell. Clear? Yeah. Today we have learnt about how to measure internal resistance of the cell by using potentiometer. The working principle is, when the galvanometer shows zero deflection, EMF or a potential difference across the cell becomes equal to the potential difference between junction and moving contact position. So that is the thing. Yeah. One more thing. Yeah. For personal class or doubts clearing, you can contact this number. So that is, yeah. Yeah. Thank you.